I guess we'll... I'll do better than cracking a joke. I actually have a little tiny story. But when Dilm actually approached me a few months ago and asked if I wanted to be part of this very high-profile event, like Andy Weiner, I couldn't imagine any answer other than, when may I begin to prepare? And although it was a little bit intimidating to think of addressing, an audience of this distinction, I had just recently come from addressing the most skeptical audience that I could imagine, which is an audience of system administrators. And I had spoken to them about cloud computing, and it went okay. So in a moment of hubris, I thought, yeah, sure, I can handle that. And then as the session came together, and I realized that I was going to be followed by, the three speakers who I could sort of think of as rock stars working in this area, I was like, I'm glad to be the opening act. So with that as a backdrop, if we could get the... Did somebody steal my video thing? Okay, who's the... Well, somebody appears to have stolen my video adapter.
This should work for you, right?
Not only that, it's mine. See, it's got my email address on it.
I just wanted to be helpful and for everybody to know it.
Thanks, Luis.
My bad.
No, that was just your way of seeing what happens if I can do this under a little bit of pressure. Okay, now, with that as a backdrop, I'm going to try to set the context for the three speakers who are coming after me. And I think my goal for this talk is for those of you who do work in computer systems research and who have had firsthand access or exposure to cloud computing, I think this subgroup of engineers, those of us who do that kind of work, 40 years of Moore's Law, 5 orders of magnitude improvement and everything, we're really jaded. So my goal, if you're part of that audience, is to remind you that I think this is not just another thing. It's not a flash in the pan. This is a serious change. Without giving away too much of the climax, I think this is like the microprocessor. I think it's potentially really that transformational. For those of you who don't work directly in that area, hopefully I'll make you aware and maybe excited about some genuinely new opportunities for problem solving that are really, I think, going to change the landscape of how people do science and engineering, even those of us who are not computer engineers per se. And for those of you who are also educators, this is changing the game for us already at Berkeley in the way that we do undergraduate education, again, both in science and engineering specifically, and also in computer systems research. So if you walk out of here with some ideas that you didn't have before and think this is maybe a larger opportunity than you might have realized, I would love to talk to you more in the halls. So to that end, I'm going to start with a slightly provocative advertisement that might appear in the not too distant future. Get your own supercomputer. And you can get a supercomputer that does nearly 42 teraflops on LinPack, very respectable benchmark for supercomputing. This would put it in the middle of or top third of the top 500 supercomputer list. There's no batch queues. You get the supercomputer, you can start running your job in minutes. There's no grant writing. All you need is a credit card. $1,400 an hour, and there's a 1-hour minimum purchase, please. There's no need to predict in advance how much usage you'll need. You just pay as you go. The more you use, the more you pay. And if you need more, you can just get more pretty much on demand. In fact, you could lease several of these simultaneously if you've got more than one experiment to run. And as far as software, well, right now we just have MPI, MATLAB. There's a few other things, but the software is getting better all the time. So the only thing on this slide that's not really true today is the scale of the supercomputer, the 41 teraflops. Not that you can't get that, just that most of us are not yet at the point where that many teraflops are being made available on a credit card basis. But a substantial fraction of that is available, and if you scale down that number by a factor of maybe 3 or 4, you could do all of this today. So where did this come from? Again, since my job is to set context, Luis Barroso is going to talk a lot about warehouse scale computing. But I think for the purposes of this backdrop, the important thing is that these enormous data centers, really unprecedented in scale, have been built to support initially consumer demand for things like web services, email, social networking. Facebook now claims 500 million active users. That's a lot of computing power to support that kind of load. So we've seen the build out of what are now, in the current parlance, being called private clouds. They're owned by particular companies to run that company's software and services. And one of the reasons that the public cloud computing, which I'll describe on the next slide, has now become available is that it turns out if you're actually buying equipment, computer networking, computer hardware, even human resources to administer those computers, when you're buying at this scale, you can see economies of scale of factors of 5 to 7 compared to provisioning the same type of equipment for a data center of order of hundreds or a couple of thousand machines. So the warehouse scale buying power is what's really allowed this to happen. And in fact, as I'm sure many of you have seen on the blogs and in the news, the latest trend is not to fill buildings with computers, but rather to containerize them and then fill warehouses or even parking lots with container-sized computers and sort of build data centers out as you go. So this is kind of the direction things are headed, and Luis will have much more to say about this. But in general, this is where we're coming from. And I think this factor of 5 to 7 is a pretty important ingredient of why in 2008, as opposed to 5 or maybe 10 years before, public cloud computing finally arrived. So the question of the minute, as Ali said, what is cloud computing? We at Berkeley sort of arrogantly wrote this paper where we decided to define what it was because there was so much confusion that we thought it would be worth at least drawing a few lines in the sand. But roughly what it means to us is that anybody with a credit card can go and more or less instantaneously acquire a more or less arbitrary number of computers on demand. There's a few different sizes that you can choose from, and they vary in terms of how many microprocessor cores and how much memory they have. But the important thing is that it's completely on demand. It's available to the public. Unlike the grid, you don't have to run special software. You don't have to be part of a consortium. All you need is a credit card. The price varies from maybe 8 cents an hour up to a couple of dollars an hour, and you pay strictly as you go with a credit card. You just get a bill every month. In fact, if you're willing to share your machines with other people, they can be as cheap as 2 cents an hour. And if you're willing to get kicked off a machine when a higher paying customer comes along, there are sort of market bidding based systems now where you can actually get machines for less than 8 cents an hour all to yourself. And the machines are provisioned and booted within a few minutes. You can start using them right away. It's pick the OS you want, install the image, boot, and go. And the big thing, what was not obvious to us when we started doing this, but in retrospect should have been, is this pricing model means you can run 1,000 machines for an hour for the same amount of money as running one machine for 1,000 hours. And we had to sort of repeat that to ourselves a few times to realize what a transformational thing that is in IT. Being able to use an immense amount of aggregate resources for a small amount of time, and in fact, if you think about it, when you do, for example, a search on Google, you actually are using one of the world's fastest supercomputers for milliseconds. So you get a very short slice, but the aggregate amount of power you get during that slice is astronomical. This is now an extension of that same idea, but at the level of jobs. So this is pretty cool. So what's in it for you? When cloud computing sort of came out in 2008, most of the attention was things that were of interest to web startups. If you're a web startup, this is great because you don't have to provision your own data center. But if you're not doing web stuff, why would you care? Well, what happened was as researchers started to catch on that this was a possibility for doing new kinds of research, some of which I'll briefly describe, new tools began to develop that would support not just, for example, running a website, but doing large batch computations. And once that happened, enterprise applications, corporate email and so forth, realized, we could start moving some of this stuff out of our own data centers and have it run better. So those applications began to develop their own ecosystem. Educators, especially within science and engineering, caught on and realized there's a possibility not only to expose students to this great technology, but to allow them to do experiments in a lab setting that there's no way they could have done with university resources. So those tools began to arise. And what we think may be happening is it's now the time for scientific and high-performance computing to get in on the action. So I'm going to spend most of the rest of the talk speaking about how scientific and high-performance computing could potentially benefit from this. So what the claim we make is that this combination of very low cost, 8 cents per hour, on demand, you can get more capacity more or less whenever you need it, and this cost associativity, where a large number of machines over a short time cost the same as a few machines over a long time, will lead to a democratization, essentially, of supercomputing capacity. So this is a goal today. We're not quite there, but I'll talk about some of the progress. The way that we're getting there is sophisticated software and operational expertise, much of which has come out of the experience of private companies like Google and IBM and Amazon who have had to acquire this expertise for running their own services. And the sophisticated software and operational expertise are used to mask the reliability of commodity components. So this allows us to build extremely powerful machines out of cheap commodity parts and actually get useful work done on them. And as one example, I won't walk through an example of the algorithm. Maybe some of you have read about this in CACM or in the literature. MapReduce is a kind of a success story that sort of deserves half a slide of its own. Originally, MapReduce are constructs in the Lisp language, and a brief description of how they work would be that they allow you to elegantly express data parallel operations, operations where you're doing the same thing on large collections of data with fairly straightforward, elegant sequential code. And in 2004, Google presented a paper describing how they had essentially implemented this abstraction, but at a scale where it would work over thousands of computers. Ever since then, a tool called Hadoop has been developed by the open source community, which tries to replicate some of that functionality in free software. But the key idea behind these tools is that the engineering to provide failure masking when machines fail, to adapt to changes in the topology, if you add or subtract machines from your cloud computing, all of the resource management necessary to do that, that's all built into the abstraction. So if you're an application writer, you don't have to deal with that. From your point of view, the complexities of dealing with some of these warehouse scale computing issues are hidden from you, and the abstraction just sort of works. So this is a good blueprint and a good success story for how to move forward. And as I said, MapReduce is just one tool. I'll talk about some applications that are using it today. But it's a good blueprint for the kinds of things that will have to happen in order to move forward and allow more science and engineering to be done using this kind of facility. So MapReduce in practice, who's using it? One example is spam classification. We're actually doing this work at Berkeley in collaboration with Twitter. And the idea is that we want to train a classifier to understand which URLs are spammy and which ones are legitimate. So as an example of how do we do this job on cloud computing, we're talking about a little more than a half a terabyte of data to train our classifiers. And if we fed all of that training through a single heavy-duty server, sort of the beefiest server we have on campus, it's about 270 hours of compute time. Or for a couple of $100, we could get the same results essentially in 3 hours. Because training for spam classification parallelizes really well. Batches of them can be farmed out to each machine and essentially done separately. So that's a local example for us. But again, the difference between getting a research result in days versus a research result in hours, that's a qualitative difference in how you do research and in the pace of innovation. Other research that we know of that's using it, genetic risk analysis and simulation at Harvard Medical School has been successfully using MapReduce for some time. Genome sequencing, IR research, the muon solenoid experiment. These are just sort of the highest profile of a list of dozens that are available now. And in some cases, they're running MapReduce or Hadoop, its open source equivalent, on university-operated clusters. In other cases, they're using a hosted version of the service that's offered as a turnkey solution by Amazon, among others. So people are already starting to use this and really integrate it directly into their research. So if this is so great, why doesn't everybody do this, right? What's the downside? Well, one big downside, just cloud programming in general is hard. Parallel programming in general is hard. And I said that MapReduce was elegant. I didn't say that it was necessarily intuitive. So there's some problems sort of naturally map onto a MapReduce kind of paradigm. But there's a huge challenge, given an existing algorithm, of identifying where the parallelism in that algorithm lies, and ideally, if it's, it has to be embarrassingly parallel for MapReduce to really be effective, right? It relies on a lot of tasks being able to be performed entirely in parallel. They don't have to talk to each other, and only at certain well-defined computation boundaries is communication necessary. So the price of using MapReduce is, can you recast your algorithm into this very specific form? And rewriting your problems to expose that kind of parallelism, even if the parallelism is there, which it sometimes is not trivial. So in fact, a pessimist would say, MapReduce is great, it solves these incredible engineering problems at scale, but from the point of view of productivity of programmers, people who want to do science and engineering, they don't want to think of themselves as programmers, this is really still a little bit closer to assembly language. We're not at the point of having super high-level languages that allow us to really just concentrate on the science and not worry too much about the programming. So the tools, admittedly, are still perhaps a bit primitive, but they are progressing rapidly. MapReduce is already quite successful. There are tools like Pig and Hive, which allow you to essentially write database-style queries. If you've ever mined a collection of database information using SQL, these are languages that allow you to write SQL-like queries, which are ultimately transformed into MapReduce structured jobs. There's middleware that we're developing at Berkeley called Mesos that allows a single cloud to be shared among MapReduce jobs, MPI jobs, and interactive jobs. And these open source tools could still integrate a lot better than they do, but the bottom line is these tools are hard to create. Again, Luis and YYZhu will have a lot to say about some specific issues that come up and how they've been handled. Parallel software is just hard. So, the open source tools are getting better. They still need to be better integrated. They still need to really address the scientist and the engineer at a higher level of productivity. But I think the promising early successes of tools like MapReduce are pointing us in the right direction. And by the way, in my other life, during our Get Acquainted session, I work on parallel programming for many-core and multi-core. And if I changed a few terms here, pretty much the same challenges would apply, right? Parallel programming is hard to do, even if you can find the parallelism, which sometimes you can't, and even if you know how to rewrite your program to match the underlying system architecture. Another challenge is big data. One of the nice things about cloud computing is that you've all of a sudden got cycles that are near the enormous storage capacity. And just to pick a few high-profile projects, from DNA sequencing, which generates around 1 terabyte per day, up to the Large Hadron Collider, which is projected to generate up to 60 terabytes of raw data per day. What do you do with this data? How do you get the data to where the computing is so that you can do stuff with it? So this is still a challenge, because if you sort of look into cloud computing economics, long-haul networking is still the most expensive aspect of cloud computing, and it's the one whose price performance is improving the most slowly. So as an example, copying a mere 8 terabytes from Berkeley to Amazon over a typical long-haul network would take about 35 days of copying time, and Amazon will charge us around $800 in transfer fees to do that, based in part on the fact that it costs them a fair amount of money to provide the long-haul networking capability. So and 8 terabytes is nothing by the scale of these data sets. So what's the solution to this? When we did the Above the Clouds paper, to which Ali and Dilma referred, one of the things we suggested, not entirely jokingly, is you could put the disks in a big box and just FedEx them, and then someone at the other end will unpack them and plug them into a rack. And a few people snickered at that, and in fact, Amazon now provides this service. You can ship an 8 terabyte drive to them, and it takes about a day and $150 in shipping and transfer fees. They will copy your data into their data center for you. So, who knows what the future of long-haul networking may be, and that's as much a policy as a technical issue. But in the meantime, this is not necessarily an obstacle to being able to do computing over immense data sets. Another challenge, what I'll call non-cloudy scientific codes. I'll have a little more to say about this when I get to sort of, bang my own drum as somebody who comes from the web community. But as cloud computing was beginning to be the subject of a lot of blogosphere hype, we would go talk to people who did scientific and high-performance computing, and what they'd say is, well, it's great. Web software is already structured to take advantage of the cloud's architecture. Scientific codes don't have that property. For example, scientific codes are often written under the assumption that they'll run on a very highly reliable machine, as opposed to this commodity hardware which flakes out all the time. That the configuration of the machine doesn't change over the lifetime of the job. Again, a reasonable assumption if you're lined up for a supercomputer, not so much if you're using commodity parts where other people are bidding for them and maybe you've got a discounted one, someone will pull it out from under you. Do you have exclusive use of those resources during the time your job runs? Again, with cloud computing, you certainly can do that, but there are significant economic incentives if you can figure out how to structure your job to opportunistically take advantage of spare resources that other people are temporarily not using. So all of these assumptions are, in many ways baked into a lot of the scientific codes that people run today. We see that in the research community as an opportunity. There's an opportunity to think about resource management in a new way that is really more fitted to the cloud computing constraints of resources may disappear out from under you. You have to deal with commodity parts that don't all work consistently. And by the way, I think we'd point out that the time to answer may still be faster, even if you choose to do this. Remember that there's less custom programming to be done because you're taking advantage of a lot of existing open source and commodity software. There's no wait. As soon as you provision your mini cloud or your mini cluster, you can start running your jobs immediately. You're not in a queue behind anybody. And if you decide a few minutes into the experiment that you've seen enough and you need to change some data and start it over, you can do that. And you can do that with a level of responsiveness that's comparable to what you get on a desktop PC. So, there's certainly a trade-off here, right? There's the way of thinking, and I work a lot with guys who do HPC and supercomputing. There's a specific way that people seem to think about writing code for a supercomputer, and it's based on the assumption that the thing you're optimizing for is the short amount of time you get to use the resource because there's so many others lined up to use it behind you. Writing software in this world is different because now, for the first time perhaps, we can do real science but think about optimizing for programmer productivity. And your absolute running time of your code may not be as fast as highly tuned code running on dedicated gold-plated hardware, but in many cases the time to answer may still be faster. And this is something that I think is currently an underappreciated facet of cloud computing. Lastly, cloud vendors, Amazon, Google, and others, Yes, it's true. Initially, they were really targeting the web and web startups and so forth, but they're now listening to HPC customers. They understand that there's a huge demand by people who want to use this as a resource for doing science. And in fact, just a couple of months ago, Amazon announced the availability of a new type of computer available in their cloud computing infrastructure. They call it the cluster compute instance, and it's essentially provisioned to resemble a high-end cluster that you would use to run high-performance scientific code. This is the one that I referred to on my first slide. It really did achieve nearly 42 teraflops on LinPack, very respectable. That was using 880 nodes, which right now, if you actually want 880 nodes, you need to make a phone call to them first. You can't just plunk down a credit card for that many. But the same thing was true when they started their regular cloud computing. You were limited to sort of 10 nodes at a time, and as they've grown their facility, that limit's gone up. So at Berkeley, we routinely do computer science systems research, and we've published results where we can demonstrate something, resource management on a 1,000-node cluster. There's no way a university could have done that even a few years ago. So this is a game changer for research as well. And MathWorks, which is the maker of the extremely popular MATLAB software, has said that they will be supporting MATLAB in the cloud on these instances. So again, the software tools are slowly catching up to where the cloud computing hardware is getting us. Better education. I know that not everybody in this room is an educator, but many of us are either academic educators or we serve an education function in a corporate setting. Cloud computing is a great fit for university courses. A lab assignment is due, everybody needs machine time. After the lab assignment, it's handed in, nothing happens for quite a long time. So besides the fact that there's an obvious match to capacity on demand, the other issue for us is that we can enable students to run new kinds of experiments. A classic experiment that you'd like students to run if they're doing internet software as a service is load balancing. How many servers of type X does it take to overload one server of type Y that's doing a critical task? It turns out that the ratio is roughly 10 to 1 for interesting configurations. So for students to discover this fact, if we need 10 computers per student for a class of 50 students, that's 500 computers. For a university, it's pretty much impossible. With cloud computing, it's a couple $100. In fact, it's less because cloud vendors are being very generous about donating usage time on the cloud for academic purposes. It unburdens the system administrators. The system administrator used to be in the critical path for every course. Please install that courseware. We need that library. You're so busy. Now we just provision our own machine images and we launch them, and the system administrator has a slightly longer lunch break. Everything goes faster. Students get access to better hardware because the cloud vendor is having to turn over their hardware all the time. They're using machines that are actually a lot more up-to-date than what they would get in the university setting. So Berkeley has started using cloud computing in a lot of EE and computer science courses, everything from the entry-level second semester freshman course up through PhD graduate experimental courses. And if this is something that you're interested in, please talk to me because it's better, but cheaper, but faster. It's really been a game changer for us. So where does this leave us? I want to close with an analogy that I can actually relate to because 1995 was around the time I was a grad student, heaven forbid, and I was part of the Network of Workstations project at Berkeley, whose whimsical logo shows a school of tiny fish representing commodity PCs about to devour the mainframes and the vector supercomputers and the symmetric multiprocessors. And the idea, the Now project did a position paper that said, these clusters of commodity PCs are going to take over the world because they have these potential advantages that you can scale a system incrementally rather than provisioning it all at once. You can scale to an absolute size that dwarfs the largest supercomputers, and this is still true today. In fact, when we talk about the largest supercomputers today, a great many of them are built out of commodity clusters. And there's the economy of using not only commodity hardware, but commodity software, commodity operating systems, open source tools, and so on. The skepticism was that these potential advantages would only be realized if you could overcome the same architectural challenges I talked about before in the context of MapReduce. Now today, when we talk about the cloud, people say, oh, web applications, sure, it's great for you guys, but it doesn't work for my code. What people forget is that in 1995, it didn't work for you guys. In 1995, web applications ran on symmetric multiprocessors, and it was not at all obvious that those applications could be restructured and refactored so that the software architecture would be a better match to the hardware architecture of a cluster, thereby turning the potential advantages into actual advantages. That was 1995. In 2010, we have a course at Berkeley where Berkeley undergrads prototype something in 6 to 8 weeks. They deploy it on cloud computing, and it's of a sophistication comparable to what it would have taken many engineer months to achieve in 1995, and they're using off-the-shelf tools to do it. So there's no magic. fellow engineers. There's no magic, it's just engineering. It took years to understand how to get the tools right and how to do that refactoring, but every time you use Google or every time you use a large-scale service, you're seeing the concrete benefits of having done that. There's no reason in principle that scientific computing can't follow a similar path. So with that, I would like to leave you with the hope that this is a democratization of supercomputing capacity beyond, I think, what we've seen. Even now, with the state of the art of today's hardware and software, the time to answer may be faster, even though the hardware isn't yet. So if you're thinking about writing a grant proposal around a supercomputer, maybe it's time to evaluate whether some part of that work could be done on commodity computers. The software and hardware are getting much better. In fact, not only are vendors listening to the HPC community, because the vendors are listening, the HPC community has an opportunity to influence the design of commodity parts. This is brand new. HPC has historically been a pretty high-end specialized niche. Now, HPC could be the thing that helps drive the design of what's going into large data centers. So we believe, I think without too much exaggeration, the democratizing effect of this may in fact be comparable to the microprocessor. With that, I would like to acknowledge, by the way, we wrote the paper. I'm one of a number of people. Engineering is a team sport as far as I'm concerned. So my colleagues in the Rad Lab that helped us do this, only by staying in very close contact with a lot of companies do we manage to try to keep our work relevant. So I would like to acknowledge them, and I would like to thank you all for being a wonderful and attentive audience. And I think I'm on time.